Good morning. In the last session I talked about the location and direction of cracks in different cast products, whether it is billet or bloom, round or slab. What are the locations and the directions? So I talked about two broad areas. One is the surface crack, which are visible on the surface of the cast product, whether it is billet, bloom or slab or rounds. Another is the internal crack, which normally you cannot see unless you take a sectional view of the cast product. That means you have to cut the product, whether it is billet, bloom, round or slab, in the cross section to have a view at the internal cracks. So surface cracks you can see on the surface of the cast products, so straight away you can have some idea of it, but for internal cracks normally you have to take a sectional view. And what I have mentioned that related to their interdendritic hot tears. So basically those interdendritic zones are relatively weak. So those areas there is a rupture, there is a crack formation, tearing at high temperature. So we call it interdendritic hot tears caused by strain in the solidifying shell exceeding critical limit. So as I have mentioned several times that the shell, solidifying shell, during solidification even after that it is undergoing some strain, lot of strain. Strain can come from different sources I have mentioned. From the ferrostatic pressure, that can be one type of strain. From the shrinkage, there can be another type of strain. From the delta to gamma transformation, where it takes place is important, at what temperature it takes place is important, there can be some strains. Then there can be additional mechanical strains due to bending of the strand, due to unbending of the strand, that means straightening. So all these will cause generation of lot of strain on the solid shell. So it depends what is the magnitude of the strain, what is the type of strain. If it is tensile, then it is a matter of concern. All of you know the tensile strain or stress will cause crack formation. So we have to be careful about all these strains. They should not exceed a critical limit. This critical limit depends on the type of the material, of course. For different type of materials, the critical limit changes. But what is important is the strains should not exceed certain limits. The strain which is imparted on the solidifying shell, whether during solidification, after solidification, due to ferrostatic force, due to shrinkage, due to delta gamma transformation, or it may be mechanical strain due to bending or unbending, straightening of the strand. So all these are important issues we have to keep in mind to get a good quality cast product. Now I have mentioned that internal crack, it can be located at somewhere midway, at the diagonal, maybe at the triple point or at the central line. Now the central line crack or central line defect, shrinkage, it is very difficult to avoid. Why? Because the last portion which is getting solidified, obviously it will have some amount of segregation. Whatever aluminium elements you have will definitely segregate. It is a question of more or less. So if you have elements like phosphorus and sulfur I have mentioned, you will have extensive segregation, and the central portion which is solidifying at the last will have relatively more of this segregation. There will be shrinkage at the location of the center. Why? Because that is the last area which is going to be solidified. So at the center line you can have both segregation as well as crack. So now what you can do in the normal circumstances, you cannot avoid center line segregation and crack. Only thing what you can do is you control the undesirable elements like sulfur and phosphorus, so that you can have less amount of central segregation, less amount of what is that called, the change in the or the depression of the solidus temperature. And what you can do is you can use low superheat casting, so that you can have more equiax zone at the center. So this cracks and segregations, they get distributed and do not concentrate at the center line. If you have, I have mentioned, if you have equiax zone at the center, you have less amount of central crack and central segregation, because what is happening is this is getting relatively distributed. But if you have columnar zone extending to the center of the cast, why the columnar zone will extend? Because of high superheat. If the superheat is high, the columnar zone, which starts from the surface of the cast product, will extend till the central portion of the cast. So this is a matter of concern. So we have to do low superheat casting. We should have low amount of phosphorus and sulfur. We should have more amount of manganese by sulfur ratio, so that the segregation of sulfur, deleterious effect of sulfur, can be taken care of. In spite of all these precautions, there will be some amount of segregation, and there is a possibility of central line cracks in the cast product. Like as I was telling you, so if you look at the internal defects in billet, bloom or round, or even slab, I will come to slab. So you can have, this is particularly the central line crack or segregation at the center of the cast product. You can have this. So it is normally, if it is a long product like billet, bloom or round, or even in slab, so it is more of longitudinal nature, that at the central location you will have crack as well as segregation, so which is called central segregation or center crack. Similar is the case for slab. Yeah, this is the central line crack or segregation. Normally you can have both crack and segregation. So why the crack is forming predominantly at the center? Because there is extensive shrinkage towards the end of the, this is the last area which is getting solidified. So there is shrinkage, solidification shrinkage, and moreover this area is relatively more more, what should I say, more, this is having too much of segregating elements because of high segregation. It is impure elements, purity is relatively less here. So this area is relatively weak. I have mentioned you that this triple point, these diagonals where the solidification fronts are meeting. So central area, again the solidification fronts are meeting, and moreover if you have columnar zone extending till the central portion, so you have additional chances or higher chances of formation of central crack and segregation. So even if you take some precautions during normal casting, what are the precautions? You use low superheat, you have less amount of phosphorus, less amount of sulfur, high ratio of manganese by sulfur. Using this you can have less intensity of segregation and crack formation at the center. Nevertheless, you will have some amount of segregation and some amount of shrinkage crack at the center always. So what do? This is a very important defect. This is a very typical defect for cast product, and for certain applications you do not want that there should be a crack or heavy segregation at the center. So some attempt will be necessary, additional precautions will be necessary to control the incidence of this crack and segregation at the central line, at the central location. So what is that? This is called mechanical soft reduction. I have mentioned that normally the the last portion of the cast product is basically almost horizontal. That means initially the solidification is starting in the mold when it is vertical or curved, depending on which type of mold you are using. Then it is coming out of the mold, and if it is a curved mold, then you require only unbending or straightening of the strand to make it horizontal. And if it is a straight mold, So, first you require bending and then unbending or straightening to make it horizontal. So, in the horizontal section, finally when the horizontal movement is there for the strand, the cast product. So, there the thickness, that means the dimension which is perpendicular to the longitudinal direction. So, that is called the thickness. So, the thickness is determined by how much gap you are giving between the different rolls. The rolls are basically used in the strand to keep the shape of the strand okay, to give the proper dimension to the strand. So, now look at what is happening if you want to do soft reduction. Soft reduction basically means you are introducing intentionally a small amount of mechanical reduction in the central portion, in the portion of the, in that portion of the strand when it is getting finally solidified. The strand has started from the mold, it has come out of the mold, solidification front is slowly increasing and finally reaching the center point. So, the area where the final solidification is taking place, that area is very important, because in that area, that zone, you are likely to have segregation and crack. Segregation due to partitioning of the alloying elements I have mentioned. So, this phosphorus sulfur which will give you heavy amount of segregation. So, the control is necessary, but even if these elements are less, even if the manganese sulfur ratio is more, then also you can have some amount of segregation. Segregation may be there also from other elements like carbon, like these are part of the chemistry of the grade. You cannot avoid them. Steel is not just iron, it will have some amount of carbon depending on the grade and the composition, desired composition. You may have manganese, you may have some silicon, you will have some amount of maybe other alloying elements, you may have titanium, you may have small amount of chromium, you may have small amount of molybdenum, you may have small amount of nickel. So, all these elements there is a possibility of some segregation, and as I have told you, the amount of segregation is more towards the end of the solidification. If you remember correctly, there is a term solid fraction in the segregation shale, modified shale relation for segregation. So, the last amount of liquid which is going to be solidified in the final central region of the cast product is relatively having more amount of solutes because of segregation. And again at the last stage of solidification there is going to be some amount of shrinkage, always will be there. Shrinkage has started during the solidification itself, but the final shrinkage always will be there in the last portion of solidification, last area which is solidified. So, in the central area, this is the, you are looking at, this is the longitudinal direction. That means whether it is bloom or billet or slab, it is going like this. Solidification is continuous casting is taking place in this way. That means the direction of casting is this way, it is coming out, is going this way. Now look at the central area where the final stage of solidification is taking place. This is the liquid, this is the mushy zone. I have mentioned about you what is mushy zone. It is basically solid and liquid. So this is the liquid, this is the mushy zone, and these areas are the solid which has already formed, solid shell. So you see here columnar, initially from the surface there was, I was mentioning earlier, you have columnar growth. Now how much columnar growth will be there, it depends on the superheat, or if you use electromagnetic stirring then also you can extend the, rather you can control the extension of the columnar growth and you will have some amount of equiax growth here. But anyway, here it is being mentioned, you see after columnar some amount of equiax solidification is there towards the central area, and this area is the mushy zone. So what is happening, final solidification will be taking place in this area where you have some mushy zone. Now if under normal conventional process during the last stage of solidification you will have some V shape of segregation, you have central segregation and you have central porosity. Porosity is because of the shrinkage at the last stage of solidification. Segregation is because the extent of segregation is relatively more at the final stage of solidification. So, you have central segregation, you have central porosity, and the segregation is sometimes distributed in V shape because of the because of the flow of the final liquid in this area. Sometimes they take a V shape. So, in the equiax, if you have equiax solidification in the final stage, you have a V shaped segregation. But if the superheat is more and you are not using electromagnetic stirring EMS, then as I have told you, equiax solidification can extend, or rather the columnar solidification, this is the columnar zone, it can extend till the central area. There will be no equiax zone in that case. So, in that situation, your crack formation is more extensive, your segregation is more extensive, and you may not have V segregation. V segregation is present when it is distributed, segregation is distributed, but when you have columnar zone extending till the central area, instead of V segregation you have pronounced central segregation. Segregation is concentrated at the line, central line only. So, this is a normal situation. Here this distance, this width or thickness, rather the thickness is maintained by here this rolls, which are the distance between the rolls will give you the final dimension. Now, if you can create some amount of squeezing, that means if you can generate some amount of mechanical pressure in this area, in the final area where solidification is taking place, this is very important where you give the pressure. If you put the pressure beforehand, it will be of no use. If you put the pressure after solidification is over, then also it will be of no use, rather it may generate crack. I will come to it later on. So, what is important is you put pressure only at the final stage, in the area of where the final solidification is taking place. This is very important. So, how do you decide where the final solidification is taking place? You can use modeling, you can use empirical relationship, as I have mentioned, the solid shell, how it is increasing. So, finally when it is reaching the center point, at what time and what depth it will reach. So, all this is possible to have some idea. So, from those ideas you can identify the area where you want to put some reduction. It is called mechanical soft reduction. You are giving some strain, some pressure you are inducing, but it is soft, it is not very high. If it is very high, it may cause crack formation, which we do not want. So, it is a mechanical soft reduction. You are reducing the thickness in this area by certain extent. Look at here what is happening. This was the original thickness dimension. You are putting some additional pressure in the final solidification zone. So, what is happening? The thickness is slowly coming down, not in one step, not at only one location, but slowly. That means there is a gradient how the thickness is coming down, and thickness is how it is coming down. You are putting pressure in the rolls, you are decreasing the distance between the rolls in these areas. Here it is normal to whatever distance was here, but slowly as you are coming down, that means you have reached the final zone of solidification, solidification front is coming to an end, you are trying to put some pressure, that means you are reducing the thickness, and finally it is becoming certain thickness. So, initial thickness was something like this before the final solidification front. Slowly you are decreasing the thickness, and in the process you are increasing the pressure, and finally the thickness is like this. That means you will find the thickness, original thickness has become slightly lower due to mechanical soft reduction. Now, what is the benefit of this? You see this liquid which will try to come in the solidification front. These are indicated free crystal growth. Because of this, you have equiax zone, but this is possible only when superheat is relatively low. So it is a similar situation, it is being shown here. So now what is happening? This mushy zone will be there. When there is a suction flow, that means whatever liquid is there, it is trying to get sucked. More and more is going to get sucked in this area, in the mushy zone area. And look at the difference between the two. Here the mushy zone front has certain shape. Here you see it is coming to it is completing, that means the solidification front is becoming more and more narrow because of the pressure you are putting. So what is the advantage? Another advantage is whatever shrinkage was supposed to be there in the final stage of solidification, you do not have them. So you are trying to compensate for the final solidification shrinkage by putting some soft reduction, minor amount of reduction. So the effect of this reduction will be absence of solidification crack at the final central region, absence of porosities, absence of final solidification crack. There were some porosities and cracks in the final solidification front, so you do not find them here. So you can control the extent of segregation and porosity by putting mechanical soft reduction. So this is an important development. By understanding the solidification front, by understanding what is going to happen in the final stage of solidification, people have devised this. So this is an afterthought. Initial, when continuous casting is to take place, the technology was not having the idea of mechanical soft reduction. So this is a conventional process. What happens when you do not put mechanical soft reduction? So in that case, you have V-shaped segregation, you may have central segregation, you may have central porosity, but when you are putting MSR, means mechanical soft reduction. The zone of mechanical soft reduction, again I am telling you, is very important. I will discuss this in greater detail after some time, but what is important is this MSR zone, mechanical soft reduction zone, when you are giving this soft reduction at the final stage of solidification, that is very important. So identification of the final stage of solidification is important, then only you can decide where will you put the mechanical soft reduction, what is the zone of mechanical soft reduction, what is the effective area of mechanical soft reduction. If you give mechanical soft reduction instead of this, you are putting soft reduction here, when the solidification is maybe 80% complete, it will be of no use. And if you put mechanical soft reduction after solidification has taken place, is completed, again it will be of no use, rather it might create some crack in the solid shell. So what is important is to identify the optimum zone where you have to put mechanical soft reduction. What is this zone? This zone is where solidification is getting completed, that means maybe from 90% to 100% solidification. That area is very important here, where you want to put this some amount of pressure, some amount of pressure for the soft reduction. And I had mentioned that this area is relatively prone to brittle crack formation also. That is why the pressure, the strain formation is gradual. You are not putting a sudden pressure at any point of solidification. You are putting slowly, you are putting the pressure. That is why it is called soft reduction, and that too, the reduction, there is a gradient of reduction. It is not one step of reduction, slowly it is increasing reduction. As such, the total reduction is not much, but it is also, there is a gradient, that means slowly it is increasing. So this is an important concept. Now, as I was telling you, let us try to understand how do you decide where to give the pressure and how much pressure do you give. This is again important, as I was telling you. So this is the intensity of reduction, that means how much amount of reduction you are giving. So, intensity is increasing this way, and fraction solid in the center of the strand. That means how much of liquid will be there in the mushy zone, how much of liquid will be there, how much of solid will be there. So, this and these are basically dependent. Fraction of solid increasing means the liquid core will be decreasing. Yeah. So, now you see here you are putting the starting mechanical soft reduction at certain location, you are finishing the mechanical soft reduction at certain location. Where are you finishing? Where the complete solidification is there. Beyond that you are not putting any soft reduction. The whole idea of giving mechanical soft reduction is to compensate the shrinkage porosity at the final stage of solidification. So, beyond that you do not want to give it. Okay, the whole idea is to stop the mechanical soft reduction, finish the soft reduction at the point of complete solidification, and you start it before complete solidification. That means the whole idea is to give, as I told you, the whole idea is to determine this area, the effective area. Now you look at it, if you put too much of pressure, too much of intensity of reduction, there might be formation of internal cracks, as I have told you. So, too much of pressure will generate internal cracks. If the pressure is less than the required amount, this is the area, there is no effect at all. You might give small amount of reduction in this zone, but it is of no use. So, what is interesting is that this intensity of reduction you are slowly increasing as you are reaching the solidification completion front. You see, intensity is initially less, slowly you are increasing the intensity. So, this is very important, that optimum intensity is important, optimum location where you put mechanical soft reduction is also important. If you put less pressure, insignificant pressure, there will be no effect. There is the whole idea of putting mechanical soft reduction will be of no use if it is not adequate, but if the amount of reduction is more, then you may have internal generation of internal cracks. So, what is important is this optimum intensity of reduction. So, the optimum zone is basically it contains both the intensity as well as the area. So, optimum zone means first the area where you will put the soft reduction and how much of soft reduction you will put. So, both are important. Do not put mechanical soft reduction beyond complete solidification area. Once solidification is complete, it is no point putting the soft reduction, rather it might create problem, it might generate crack. So, do not put beyond this. So, important to find out what is the optimum zone. Optimum zone means first the area in which mechanical soft reduction has to be given, and then how much of soft reduction has to be given. Initially it is less, and as you are going towards the complete solidification it is relatively more, as I have shown in this diagram. Initially you see the thickness is coming down to a little extent, slowly it is increasing and finally stabilizing at certain point, and beyond this you are not increasing the pressure, you are not decreasing the thickness, that means you are not increasing the pressure, it is getting stabilized. So, the intensity is coming to an end at this point. Slowly it is increasing from here, it is increasing, it is increasing, it is increasing, and then it is coming to an end. This is what has been shown here. The level of intensity is increasing and then finally coming to an end when the solidification is complete. Beyond that you do not put any mechanical pressure, any mechanical soft reduction. So, the whole idea is to identify that zone where there is final solidification is expected to be there, that is number one. This area is important, where you are putting the mechanical soft reduction, where you are starting, where you are completing. Beyond complete solidification we should not give mechanical soft reduction. The number one. Number two, how much of soft reaction you will give, what is the intensity of reduction, that is also important. If you give less amount of reduction, there might not be any effect, so it is of no consequence. If you use too much of pressure, there might be internal formation of internal cracks. This too much of pressure if you give, there will be internal crack. So you give pressure only to the extent which is optimum. So this you can find out by trial and error. Maybe you can use certain initially some small amount, maybe initial, then increase the amount, and then see when the the effect has started, and finally don't go beyond that. If you go beyond that, maybe you will find that there are crack generation, additional crack generation in the shell. So to control crack, porosity and segregation in the central area, near the central line, mechanical soft reduction is a very useful technology which is being used by many continuous cast users to get a good quality of cast product at the center. So this location and intensity I am again telling is very important. Now let us see what is the effect. This is without mechanical soft reduction. You see the intensity of segregation, and there may be some cracks also at the central region. These are some V-shaped segregation near the central region. So this is when you are not using mechanical soft reduction, and when you are using mechanical soft reduction, look at the central region. The intensity has come down quite a bit, and you see it is slightly, the thickness is slightly less compared to the normal situation. Why this is so? Because as I have told you, I have mentioned that if the normal thickness is this, by putting mechanical soft reduction, what you are doing is you are slightly reducing the area where final solidification is taking place. So the thickness, final thickness is slightly less compared to the what would have been the normal final thickness. This is a normal final thickness, and if you are using mechanical soft reduction, your final thickness is slightly less because you have put some pressure, you have decreased the thickness, the in between gap for the rolls, between the rolls in the final stage of solidification. So this is an important concept. So because of this, what is happening? You get less amount of segregation, you get less amount of crack in the final central line or central area. So I have mentioned that to take care of the central line crack, central line segregation, what is important is to use mechanical soft reduction. Where do you use the mechanical soft reduction? You use it in the area where the final solidification is taking place. You do not use anywhere else. You do not use at the solidification level is say 50-60%. You do not use it. It is of no use. You use only when the final solidification is taking place. So that there you are putting the mechanical soft reduction, MSR. So what is happening? The segregation at the center and the porosity at the center area are coming down, the intensity is coming down. So this is what is important. Instead of a pronounced central line, it is getting distributed. That is what is important. So the effect of soft reduction is to control the level of segregation and crack at the central line. So this is getting distributed. Instead of concentrating at the center, things are getting distributed, segregation, and porosity and cracks are almost eliminated. If you can give adequate amount of soft reduction, you may not get central porosity at all, you may not get central crack formation at all, because shrinkage is getting compensated. So, this is an important concept what I have mentioned. So, what is important is the using of optimum zone. Optimum zone means first the location of the mechanical soft reduction area, where do you put the area mechanical soft reduction, and how much of pressure do you put. So, both are important, location of mechanical soft reduction and the intensity of soft reduction, that is how much of pressure do you put. It has to be adequate, as I was telling. If it is less, it will not have any effect. If it is more than the required amount, you may have internal cracks, which is again not desirable. So, it is a combination of location and intensity which will impart the desired effect, which will give us a sound product where there is no central crack, the central segregation is not pronounced, central segregation is rather distributed. So, we have a relatively good quality cast where the central area is of desirable quality. Now, I have mentioned about the central crack and central segregation problem, that on the surface of a slab you can have some defect